Section 3.2 asks us about which point is here, and there's really not a whole lot of instruction because this is more of a discussion point that we would have had in our class together. It would have asked you to just pick a point somewhere on here, not telling anybody or pointing to which one you're talking about, but using some words to describe it to see if they can arrive at the same point that you were thinking of. So we have to be clear about some ideas, and as people do this in class, a lot of times we use some of the same language that we used in our warm-up today on Lesson 3. You might tell me about which quadrant that you're seeing. Right? So if I told you that I was thinking about one of the points on the unit circle that is in quadrant 3 and is the point closest to the x-axis in quadrant 3. You might be looking with me here into quadrant 3 and finding the one that is closest to the x-axis, and maybe you would realize that I'm talking about this point right here. We need to bring up a couple standards that we're going to use every time that we're talking about angles, because that could get really wordy if we don't have a better way to describe what point we're thinking of. So we certainly know about our quadrants. Quadrant 1, quadrant 2, quadrant 3, quadrant 4. And you may see this in Roman numerals. 1, 2, 3, and IV means 4. That's 1 less than 5. So we can think about what quadrants they are. As we start, though, thinking about angle measures, we have seen in geometry a lot of angles that named them based on what was at the center. But because we're going to be using this unit circle so much, there is no point at the center, and it could be any angle there. So a lot of times if they had like an angle that looked like this, they would put a point there and they'd call it angle R. Alright, and so they might tell you how many degrees angle R might be. They also might have used something like angle theta. It's a good word to use here. So this is the Greek letter theta, T-H-E-T-A. And on our graphing calculator, you may have noticed this and you might not have even realized we have been talking about it all along. Here, in our variable button, it has an x. We're used to having x be our variable. But this third one here is actually the theta. It means angle. So we're going to start seeing in our future, especially in this unit, maybe we have an unknown angle that we're going to be graphing. And as we start making some changes and some things about what we're looking at, it might be that we are using we're going to start seeing what some signs of those angles might be, right? So we can start graphing sines, cosines, and tangents. It's just a little preview about what we might be having in our future. I'm getting it ready on my calculator so you can see what that's going to look like. But I went to my y equals. And I have the sine of x because that's the same thing as our unknown, our theta. And when we look at our graph, there's that cool sine wave that I kind of drew on the intro of this unit. So it's coming forward. We'll see where it comes from, but we use that as the word theta. We always start our angle measures in math from this horizontal line, right from the x-axis. Just like we would start our coordinates with x's and y's, we do the x first. When we're thinking about an angle, we start from the x-axis, and it's a matter of how many degrees, or sometimes we use a measure called radians, that might describe how far we've gone. So if I had to guess this, let's see, this is definitely more than 90 degrees, not quite 180 degrees. So maybe that's like 135 degrees. Okay. So this point was really just getting us to say, well, wouldn't it be so nice if we could name these things a little bit better? just the idea that we start here on the x-axis, we move in a counterclockwise direction as we're describing angles. So this would be a positive 135 degrees if we started here at this x-axis and we moved downward. Something like this angle here might be called a negative 45 degree angle. Okay, so it starts here and it moves in a negative manner instead of starting here and moving in a positive way. This next part is also a little bit conceptual going on here. So it says your teacher will give you a circular object. I'm using this nifty little cup. It's a Tupperware cup, very much a circle going on. So I'm giving myself this circular object. And we want to think about how many radii does it take to go halfway around this circular object. Boy, would it be nice if I had something that could measure that radius. Oh look, I have this nifty post-it note. So this post-it note goes almost exactly across that diameter. Okay, so it's almost a perfect match. Kind of nice. When I think about this, though, I'm not looking for the diameter, I'm looking for the radius. And so the radius is right about here, right in half. Now we're not going to be perfectly exact here. We certainly could be. I could fold my piece of paper in half, knowing that it's almost an exact diameter, and then say, hey, that line right there, there's our radius. Okay. So if this piece of paper is the radius that would go from that center around that circle, I want to see how many radii it takes to get halfway around the circle. And so I'm just using my little post-it note to mark off radii here. So now that I have this kind of exactly in half, I'm going to use my newly formed tape measure. I have a total of 4 radii in length, and it asks me about how many radii does it take to go halfway around the circle. Well, if I start right here and I roll this around the circle, and I need a little piece of tape to keep this going. So I've gotten myself definitely more than halfway around the circle, right? You can see how much I've gone around, and it's definitely too far. So 4 radii is definitely too much. But if I were to look about halfway across the circle, it would be right about there. So I'm just using my pen to kind of look at that halfway point across the circle, and I put a little mark on the inside there. Now notice it is just past my halfway point. So I have 1 radius, 2 radii, 3 radii, and then it's just a little smidge past that where I drew my pen line. You might already be picturing what exactly it is we're going for here. It is just over 3 radii. And a little hint, it's actually 3.14159. It is pi radii. That's where pi came from. Somebody said, hey, it doesn't matter what size circle I give you. Whatever that is, you find that radius and you figure out how many times around that radius would go, and you will find it's always just a smidge over 3 radii to get halfway around the circle. And so to go all the way around the circle, it's going to take twice that amount. If it took me pi to go half, it's going to take me 2 pi's to go all the way around the circle. So as we start drawing this unit circle, we will not only know that this point is 1 unit from the origin, but we will know that as we start going through here, that this length is pi rotations around. Do you see how we're moving this point from here? We'd be moving at a distance of 3.14 to get here, and another distance of 3.14 to get there. That's how we're going to start measuring these things called radians. All right. So up here we looked at them in degrees. We're going to start using pi, or portions of pi, because these points are moving around, always staying 1 unit away from the center, and so they're moving some distances based on pi. Okay. So the exact number of radii that would fit, there's that 3.14159, because we're smart. It's the definition of pi. And so this idea about why doesn't the number of radii that fit around the circumference depend on the radius of the circle? And it's because they grow in proportion to each other. Radius and circumference grow in proportion to each other. As the radius gets bigger, the circumference gets longer. Bigger radius, larger circumference. Smaller radius, smaller circumference. Let's look around this bike wheel.